Welcome back, everybody. This is section 2.4 on biconditional statements and definitions for our geometry textbook for Math 211. So for this section, we are going to talk about biconditional statements and then also look at how they're related to figuring out if a definition is good or not. So a biconditional statement is the equivalent to writing a conditional statement and its converse. For a biconditional statement, you actually take your conditional statement, take out the if-then, and then really what you do is you take P, put it first, Q would go last, and in between you would put the phrase if and only if. So here they gave us a biconditional statement, and they want us to write it as a conditional statement and its converse. So the biconditional statement they gave us is if two angles are supplementary if and only if the sum of their measures is 180. So when we look at the initial biconditional statement, the first part we're always going to say that's our P, and then the second part is going to be the Q. So if I write this in conditional form first, it would be if two angles are supplementary, then the sum of their measures is 180 degrees. Then the converse, remember, is you just switch P and Q. So it would be if the sum of, and I'm going to put the two angles first instead of the sum of their measures because you don't know what it is. So if the sum of two angles is 180 degrees, then they are supplementary. And again, the wording, you could switch it around a little bit, like something like I did. It's not going to change the meaning, but you want to make sure you have P and Q represented as they should be in your statements. Just like we looked before, our conditional statement had the single-sided arrow. Like if we had a conditional statement, it was if P, then Q. The biconditional statement uses a double-sided arrow, so it would be P if and only if Q. So you use the double-sided arrow with each statement listed. All right, so here they give us a true conditional statement, and that conditional statement is if a closed figure is a triangle, then it has three sides. So we can identify right here, we have P and then our Q. And what they want us to do is they want us to write this as a biconditional statement. But first what we have to do is to write it as a true biconditional statement, or to be able to write it as a biconditional statement, it means that both the conditional and the converse statement both have to be true. So what we're going to do first is we're going to take and write the converse of our conditional statement. So remember, your converse would be if Q, then P. So I'm going to say if a closed figure has three sides, then it is a triangle. So now we have to look at that. is that a true statement? If a figure has three sides, a closed figure has three sides, then it is a triangle. That is a true statement. So the conditional and the converse are both true. So now we can write it as a biconditional statement. If it was not true, then we have to give a counterexample. So let's take it and write it as a conditional statement. What we need to do is go back to the original conditional statement to write it as a biconditional. So we would say a closed figure is a triangle if and only if it has three sides. And that would be our biconditional statement. All right, so we're going to do the same thing here. We're going to first look at our original true conditional statement, and that is if x equals 5, then x squared equals 25. So the converse would be to switch P and Q. So it would be if x squared equals 25, then x equals 5. Is this statement true or false? Well, I do know that if you square 5, you get 25. But I can find a counterexample. It's not the only number. I know that I can square -5 and also get 25. So that would make this a false statement. And we can say, well, I know that x can equal -5. So we can say x can also be -5. So that would be our counterexample, and we can't write it as a biconditional statement. All right, so in the past sections, I mentioned looking at a definition and what made a good definition. And now we're going to look at how can we find a good definition. And a good definition can be written as a true biconditional statement. So that means that it's the same forwards and backwards. So we can take the conditional statement and look at its converse, and it will also be true. If you have a true biconditional statement, so that it can be used forwards or backwards, this can help us with logical reasoning and to verify a part of a proof. And then again, one way to prove that your statement is not a good definition, find a counterexample. So here we have 4 statements, and they want us to figure out which one is the good definition. So our 4 choices are A, a fish is an animal that swims. B, rectangles have 4 corners. C, giraffes are animals with very long necks. And D, a penny is a coin worth 1 cent. So really what I want you to think of is think of these as a conditional statement. And then think of the converse. Is it still true? Or can you find a counterexample? So I want you to look through these 4 examples and pick which one you think is a good example. And then we're going to go through all of them and we'll check. So take a second, pause the video, pick one, and then we'll check. Okay, so first we have choice A. A fish is an animal that swims. Now, if I were to think of that kind of like a conditional statement, if an animal is a fish, then it swims. And then I looked at the converse. If an animal swims, then it is a fish. Is that true? Is the fish the only thing that swims? The answer there would be no. There are lots of other animals that swim. They gave us a counterexample as a whale. It's a mammal, not a fish. You could think of a turtle because they're considered reptiles. So there's lots of other things, creatures that swim. that are not fish. So this would not be a good definition. All right, so now we have our second choice, which are rectangles have 4 corners. And if you think about this, if a figure is a rectangle, then it has 4 corners. Or if a figure has 4 corners, then it is a rectangle. Well, that's not necessarily true. Even if I'm thinking of just rectangles, I can think of like a square, which is considered a rectangle, but not necessarily, it's more defined than a rectangle. And here for choice B, they say, well, the corners is not clearly defined. Doesn't mean that it measures 90 degrees. It could just be a 4-sided figure that has 4 corners that may not all measure 90 degrees. So therefore, this also is not a very good definition. We can find a counterexample. All right, so choice C was giraffes are animals with very long necks. So if an animal is a giraffe, then it has a long neck, a very long neck. If an animal has a very long neck, then it is a giraffe. Think about that. Most times when we think about an animal with a long neck, we do think of giraffe. However, I'm not sure what very long means. And I can also think of other animals with long necks. For instance, an ostrich has a long neck, an egret. And again, we're not sure what long necks mean. So there are other animals out there that could be have long necks. It just depends on the definition of what that is. So again, not a very good definition. All right, and now we have D, our last choice. And D is a penny is a coin worth 1 cent. So if a coin is a penny, then it's worth 1 cent. If a coin is worth 1 cent, then it is a penny. Both ways, if you look at the conditional and the converse to that, they both are true and they make sense. It's reversible. So D hopefully is the one you picked, but that is an example of a good definition. And we will see all the time when we are starting in our next chapter and a little bit here, but we'll look at theorems and they'll give us the theorem, but then they'll also give us the converse of the theorem. So really, and your theorems will be written in if-then form. And then they'll switch it for the converse. So we'll talk about this more later on in the coming chapters. All right, so the last thing we're going to do for this one is determine whether the following definition is a good one. So we're going to write it as a biconditional statement if it is. We have the definition, a right angle is an angle that measures 90 degrees. So remember, we want to write it as a conditional statement first. So that would be something like, if an angle is a right angle, then it measures 90 degrees. I'm going to write that out. So if an angle is a right angle, then it measures 90 degrees. That is a true statement if an angle is a right angle. So now let's look at the converse to that. So if an angle measures 90 degrees, then the angle is a right angle. So, and again, this is a true statement. So because the conditional is true and the converse is true, we can write this as a true biconditional statement, and it's a good definition. So we would say an angle is a right angle for the biconditional. If and only if it measures 90 degrees. And that would be a way to take a conditional and write it as a biconditional statement, and to figure out if it's a good definition. If it's true forwards and backwards, written as a conditional statement, then it is going to be a good definition. And that is it for section 2.4. I will talk to you guys shortly with 2.5.